I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Light. We usually think of it as simple, predictable, bouncing off mirrors, bending through glass, or guiding our data through optical fibers. But beyond this familiar linear world lies something extraordinary, a realm where light stops obeying the usual rules. Welcome to the fascinating world of nonlinear photonics. Imagine light changing its own color mid-flight, amplifying itself without electronics, or even creating entangled particles that make communication unhackable. This is not science fiction. It's what happens when light becomes so intense that it starts changing the very material it travels through. That's the magic of non-linear optics, where the response of matter is no longer proportional to the input light. In this regime, photons behave in surprising, powerful ways, giving rise to technologies that are reshaping communication, computing, imaging, and even quantum science. It all began in 1961, just after the invention of the laser. Physicist Peter Franken and his team aimed a ruby laser at a quartz crystal and saw light emerge at twice the original frequency. They had just witnessed second harmonic generation, the birth of nonlinear optics. Soon after, physicist Nicholas Blumenbergen provided the theoretical foundation for these strange effects and earned a Nobel Prize for it. From that moment on, scientists realized light could do far more than illuminate. It could transform. So what makes light go nonlinear? Under normal, low-intensity conditions, light passes through materials peacefully. The response is linear and predictable, but crank up the intensity, like in a laser, and the electrons inside the material start to respond in new, non-linear ways. The refractive index changes, absorption shifts, and entirely new colors of light can be generated. One of the first of these effects is second harmonic generation, or frequency doubling. It's how an infrared laser becomes visible green light, like the ones in laser pointers. Then there's self-phase modulation, where a pulse of light alters its own phase, stretching into a brilliant broadband spectrum called a supercontinuum, the foundation of ultrafast lasers and chip-scale spectroscopy. Another phenomenon is the Kerr effect, where the refractive index changes with intensity, allowing beams to literally focus themselves. This leads to solitons, light pulses that travel long distances without distortion, crucial for fiber optic communications. Four-wave mixing is another marvel, where different light waves interact to produce entirely new frequencies. It's used for wavelength conversion and amplification in today's optical networks. At the extreme end, nonlinear materials can even show optical bistability, two stable light states for the same input. This enables all optical switching, where light controls light with no electronics involved, a major step toward ultrafast photonic computing. And at the quantum frontier, things get even stranger. Nonlinear effects like spontaneous parametric down conversion let a single photon split into two entangled ones, the heart of quantum encryption and quantum networks. Modern devices, especially those made from lithium niobate, can now generate and control these interactions with astonishing precision, enabling quantum computing, secure communication, and ultra-sensitive sensors. These breakthroughs aren't just theoretical, they're powering real-world technologies today. In medicine, nonlinear optics enables multiphoton microscopy, which lets doctors and scientists peer deep into living tissues with incredible resolution without damaging them. It's transforming neuroscience, cancer diagnostics, and regenerative medicine. In industry and research, ultrafast lasers based on nonlinear effects produce femtosecond pulses that can cut, weld, and shape materials at atomic precision or capture electron motion in attosecond experiments. In telecommunications, nonlinear optics is the unsung hero behind global high-speed internet. Fiber optic amplifiers boost signals over thousands of kilometers, and four-wave mixing allows dynamic wavelength control for massive data throughput. New nonlinear materials now make it possible to process signals at speeds beyond 1 trillion bits per second, far beyond electronic limits. Inside data centers, nonlinear optical materials drive next-generation transceivers that can handle 8G-level speeds while using far less power. These systems enable faster, denser, and greener cloud computing. At the same time, nonlinear metasurfaces are transforming LiDAR systems, delivering ultra-precise beam steering for autonomous vehicles and drones with no moving parts. Even in defense, nonlinear optics is a strategic game changer. It powers adaptive laser beam correction systems that can cut through turbulence for directed energy weapons. It protects soldiers and sensors from blinding laser threats with smart, real-time optical filters. And it enhances satellite communication and radar systems through all optical signal processing and photonic beam steering. The materials behind all this innovation are evolving fast. Crystals like lithium niobate and beta barium borate have long been the workhorses of nonlinear optics. But now, new materials like periodically poled lithium niobate, gallium arsenide, and aluminum gallium arsenide are pushing performance far beyond traditional limits. Meanwhile, 2D materials such as graphene and molybdenum disulfide are showing nonlinear responses thousands of times stronger than bulk crystals, all in atomically thin layers. And silicon photonics, once thought too limited, is being reimagined with clever engineering to bring nonlinear effects onto CMOS-compatible chips. Of course, there are challenges. Nonlinear effects often demand precise phase matching and high power, but advances in nanophotonics, metamaterials, and AI-driven optimization are solving these issues. Machine learning is now being used to tune lasers automatically and optimize nonlinear processes in real time, while topological photonics offers structures that can guide light without loss or disorder. At the leading edge, researchers are even producing 50 attosecond light pulses, short enough to watch electrons move inside atoms, opening a new window into the quantum world. Looking forward, the possibilities are breathtaking. Imagine computers that use light instead of electricity, performing trillions of operations per second with almost no heat. Or environmental sensors that detect a single molecule of gas in the air. Or medical imaging that lets doctors diagnose diseases instantly without surgery. Nonlinear photonics is not just an evolution of optics. It's a revolution at the intersection of physics, engineering, and imagination. As materials become smarter and integration becomes seamless, we're heading toward a future where light doesn't just transmit information. It processes, senses, heals, and even thinks. In a universe ruled by light, nonlinear photonics reminds us that the most powerful paths forward are the ones that bend, twist, and shimmer beyond the limits of the linear world. Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.